The resource allocation graph algorithm is not applicable to a resource allocation system with multiple instances of each resource type. The data avoidance algorithm that we describe next is applicable to such a system, but is less efficient than the resource allocation graph scheme. It is Banker's algorithm. Each new process must claim the maximum number of instances of each resource type before execution. When a process requires a resource, the system must determine whether the allocation of these resources will leave the system in a safe state. If it will, the resources are allocated. Otherwise, the process must wait until some other process releases enough resources. Several data structures must be maintained to implement the Banker's algorithm. These data structures encode the state of the resource allocation system. We need the following data structures, where N is the number of processes in the system, and M is the number of resource types. So, the first matrix is available. It is a vector of length M. If available J equals to K, that means there are K instances of resource type Rj available. The second max matrix, it is N times M matrix. If matrix Ij equals to K, then process Pi may request at most K instances of resource type Rj. Third, allocation matrix. It is also N times M matrix. If allocation Ij equals to K, then Pi is currently allocated K instances of Rj. Fourth, need. It is N times M matrix. If need Ij equals to K, then Pi may need K more instances of Rj to complete its task. From the definition of max and allocation and need, we find that every element of need equals to the relative element max minus the element allocation. So we can see this one. And first, about Banker's algorithm. The first algorithm is safety algorithm. It will finding out whether or not a system is in a safe state. So the algorithm's definition is as follows. First, let work and finish be vectors of length M and N respectively. So we can see we can use a one-dimensional array to implement work and finish. Initialize work equals to available, and the finish I equals to false for I equals to 1, 2, 3 till N. Of course, N is the number of processes in the system. So that means any process in the system doesn't finish. Okay, and the second step of the algorithm, find an I such that both finish I, the precise doesn't finish, and its need I smaller or equals to work. If no such I exists, go to step 4. Then step 3, work equals to work plus allocation I. Because in this step 2, we can satisfy precise I's need. So we assume that precise I can finish its work and return its allocated resources to the system. So we have this formula, okay? Then finish I equals to 2. Then go to step 2 till we cannot find I, okay? So if finish I equals to 2 for all I, that means all processes finish their work. All processes in the system finish their work. Then the system is in a safe state. Otherwise, the system is unsafe. And the sequence you find precise is the safe sequence if the system is in safe state. This algorithm may require an order of m times n square operations to decide whether a state is safe. So you can see it is complicated. So let's look at an example. Example of Banker's algorithm. Suppose that there are 5 processes in the system. We name it as P0 to P4. In the 3 resources type, we name them as A, B, C. In the resource type A have 10 instances, and B have 5 instances, and C have 7 instances. And so snapshot at time t0, we can also say the state of the system at time t0. We get the allocation matrix, the max matrix, and the available vector. So by max matrix and allocation matrix, we use max minus allocation, we get need. This is need matrix. So now we first look at this. First, we get work. Work equals to available, and finish, all the element of the finish equals to false for precise. So let's look at